Okay.
All right.
Wait, hold on. Welcome to Math 104, everybody. This is our very first online class. We have 13 participants of the 30 blah, blah, blah. So I guess a lot of you are in bed or at work or something, or actually maybe helping out in this pandemic days. But Beck is going to talk now about her office hours for her TA homework help sessions things. Hit it, Beck.
All right. So back in the day, my sessions were Wednesday and Thursday. Wednesday from 4 to 5, and Thursday from 5:30 to 6:30. I'm planning on still keeping those times, but if they don't work anymore due to like working, helping out family at home, like that kind of thing, please let me know. Shoot me an email. I can post my email again. Otherwise, it's all over the Canvas site. Um, yeah, I'm planning on doing them over Zoom. So if you want to just double check my announcement that I had made earlier this month, you can do that. All the information is right there. But like I said, if the time doesn't work anymore, please let me know. I will do my best to work around your schedule. Otherwise, keep sending Abba, Franny, and I messages through WebWork, and we will get back to you as soon as we can. Otherwise, yeah, I'm planning on still doing my sessions. Don't worry about that, but just let me know if that doesn't work anymore. I'll probably send out another Google form just to be sure that everything is still working out. So just let us know. We're here for you. So yeah, that's all I got.
That's a great announcement. And also, she forgot the word Canvas. When she said announcements, all that information is in the announcements on Canvas, obvious, because that's what we're using. And that's it. Oh, and Fran Mama is going to get back to me. We're not sure what the SI situation is, but she's good to go still. If she's good to go still, you know. Yeah, I mean, she's got time, but we'll see if the university is still going to offer that service. I'm sure they are. That'd be kind of messed up if they aren't.
Otherwise, all you Math 20 and Math 50 folk, please come to my sessions. I've talked out with Abba a couple times, and we still want you to get help, even if some stuff is kind of falling through with the SI sessions right now. So please come to my session, say hi, we can talk stuff out, and it should be good.
Mm-hmm.
Yeah.
And then wash your hands thing. Tell them that.
Oh, yeah. Yeah. Eat healthy food if you can. Wash hands. Brush your teeth. Take showers. Do all that.
Don't lick a stranger's face who's in Walmart or anywhere.
Agreed.
Okay. Okay, let's start math. Beck, you gonna stay or gonna go?
I'm gonna head out. I got some other stuff I gotta do.
Okay.
Okay. All right. Have a great math session, guys. Hopefully see you guys soon. But yeah, just check the announcement on Canvas, and that's where you can find me. So have a good math, guys. And leave.
Okay, it's 12:08. Class is going to begin. It'll end hopefully at 1. If I go a little over, it might go over. But also, since this is being recorded, you come and go as you please. You're totally welcome to do that. I want to finish the 5.3 handout that we were doing. But first, I want to, I'm going to share a screen. So class has officially begun, so put on your class hat, whatever that. No need to raise the hand. There is a hand-raising feature, and you can use that. But since we're so few, just turn on your microphone and ask the question, then turn it back off. Okay, I'm sharing a screen now. Here we go. Okay, so we're on this handout 5.3, and I know a lot of you watching this, since there were 10 people absent on that last day of class that we had before Friday the 13th, I'm just going to quickly review some of the stuff that we know. I'm doing this fast, so if you actually missed, like some of you missed all of that week, you know who you are. You need to look at these solutions on the internet, or you can pause this screen as I'm going through, since you're watching a recording. So we're dealing with sets, and also if you know the hell out of this, then I don't know, eat crackers or something, saltines. So order does not matter when we have sets, and duplicate elements are ignored. So there's not actually 2 Z's in this set. There's only 1 Z. By the way, question, just one person answer. Can you see my cursor move, this little hand thing?
Yeah, we can.
Okay, cool, thank you. Because that'll be sucky if you guys couldn't. Okay, so repetition doesn't matter, and duplicate elements are ignored. So this set really only has 3 elements in it. We use capital letters to denote sets. Sometimes we can use words to describe them, or we can just list all the elements out. If there's infinitely many elements, that's really hard to do. This thing about set theoretic notation, I won't go over that now. If you missed that class, look over that. There's a lot of symbols that we need to know. Technical difficulty. Okay, no, there we go. Why don't I just make this full screen? That's a better idea. Oh, there we go. Oh, yeah. What a great idea. So the symbols we need to know are things like an element. Actually, let me go where they're defined. So the first symbol that we need to know is the element of this thing that looks like an E, but it's not an E, and it's not an epsilon. So C is the set of odd integers. We write 3 is an element of C, and that's how we say it. 30 is not an element of C. We draw a line through it to make sure that it's not an element. The 2 big symbols we need to know are union and intersection. And union is A union B is the set of all elements that belong to A or belong to B or possibly both. For example, if A is the set of like fish and B is the set of swimming animals, then like a dog will be in the union because some dogs can swim. It doesn't have to be a fish, you know. But then some like things like actually, I'm really bad at this example. Okay, let's just move on because I don't know what's both a fish and a swimming animal that's not a fish. Like okay, forget it. Okay. Let's see, A intersection B is the set of all elements that belong to A and to B. So the big difference between and or, sorry, union and intersection is union has or and intersection has and. And the way to memorize that is union looks like a U, and the word sounds like or. Remember that, there's a pandemic, I mean, that's like true use of like when there's a pandemic. Let's see. So an example, A intersect B. Actually, we won't do this example because in 5.3 we're going to be looking at a lot of this work. So the symbol subset, view this as houses. We have a house on the right and a house on the left, and B is a subset of A if everybody who lives in B also lives in A. For instance, this is B and this is A. I draw them as houses. There's 2 tenants in the left house, named 1 Mr. 2 or Mrs. 1, Mrs. 2 or whatever, and they are also there. Hey, there they are. Mr. 1 and Mr. 2. They live in both houses. So that indeed is a positive subset relationship. If there was, say, a number 3 in the left house, then this would not be a subset of the right house. All right. Then there's these 2. The smallest set possible is the empty set, the set with nothing in it. We note it with curly braces with nothing in it. Then there's the largest set possible. It's called the universal set, or sometimes just the universe. And that is the superset that a set's elements come from. So a superset is kind of a, well, if a subset is a set that is smaller or equal to a bigger set, a superset is something that's bigger or equal to a smaller. So the universal set is understood by the situation. So if set A is the goldfish, dogs, and cats, the universe is obviously house pets, because these are things that are, well, house pets. Complement of a set, we write A, and then we put this little thing that I call prime, A prime. It's pronounced A complement. So the symbol is called prime, but we pronounce this whole thing A complement. It's the set of all things in the universe that don't belong to A. For instance, if E is the even integers, duh, E prime is the odd integers. Why? Because the universe is understood to be all integers. Like, where does E live inside of? It lives in the set of all integers. So if you say what's not in E, you will never say stuff like 1/2 or pi. I mean, even though 1/2 and pi are not considered even integers, they are not in the complement of E, because the complement means stuff inside the universal set that is not inside capital E. Alrighty. So we write that in set theoretic notation. E prime is equal to all of the little n in the universe, such that little n is not an element of big E. So this is set theoretic notation. Little n is a dummy variable. It doesn't matter what we call it. We could have called it little a, little x, little anything. but n is a good enough letter for a dummy variable. Chime in with any questions if you have any questions, but I mean, everyone who's probably watching this, in this room probably did not miss these classes. So worked examples, look this over on your own, because, well, if S is A, B, C, and this is a universe, what's S prime? Well, everything inside the universe that's not A, B, or C. T prime, similarly the same. Let's move on. Definitely, by the way, if you missed class, please look this over. This is not trivial stuff. Popular numerical sets, again, look this over on your own on the solutions on our course webpage. But these are really important sets to know. I reopened homework 5.1 for some of you who didn't do it, so that was one of the questions that's on there. Oh, this is good for us to look at. 5 is an element of the set containing 3, 5, 7. Yes. Is the set containing 5 an element of this set? Definitely not. This set on the right has 3 things in it, and none of them is a house that has a number 5 in it. So this is false. Is 5 a subset of this set? Hell no, because the thing on the left isn't even a house. It doesn't have like a house. It's like on the left of the symbol has to be a house on the left and a house on the right, meaning like a set on the left and a set on the right. Here, this is valid, this use of the symbol at least, because on the left we have a house that has 1 tenant, on the right we have a house that has 3 tenants, and yes, 5 does live in this house. Whoops. Whoop, whoa. Oh, that was interesting. Is 0 an element of the empty set? No, empty set is empty, so nothing is in it, including the number 0, which is something. This is a bit psychedelic down here. Is the empty set subset of this set? Yes, that's true for all the time, because everybody who lives in this house, who is nobody at all, also lives in the right house. Right? Remember what I said in class, every single purple elephant in this classroom is wearing a tutu. That's a true statement no matter where you go, because you never see a purple elephant wearing a tutu anywhere. So you can say every single elephant in this room, purple elephant, is wearing a tutu. It's a true statement. This is called vacuously true statement. Everybody who lives here also lives here. Why? Because there ain't nobody who lives here. All right. This example, look this over on your own, because we're going to do an example like that in the 5.3 worksheet, which we're on. Why was this unanswered here? How many elements are in here? No, there are no elements in this set. How many elements are in the set containing a set that has nothing in it? Well, there's 1 element in this big set. In fact, the element itself is an empty set. How many things are in this set here? Well, this is a set with 2 objects. One object is an empty set. The other object is a set containing an empty set. So there's 2 objects there. That's a little psychedelic. Principles of counting. How many things are in a set? We denote that little n of s, or a big N of s, or absolute value of s. We're rarely going to ever use these in class, but if you're going to steal stuff from the internet or look at other sources, you'll see both of these things. So if this set has clearly 3 things in it, this set clearly has infinitely many things in it, and this set has nothing in it. 0, zilch. Let's see. Things get expressively harder. So again, if you missed class, understand why there's 3 things in this set here. There's this empty set, there's a set that contains the empty set, and then there's this 3rd thing. It's a set that contains the empty set and the set containing the empty set. Woo! Ain't that a doohickey, or whatever the word is. Hey, does anybody, okay, feel free to chime in. There's something wrong to the right of this equal symbol. There is a typo. What's the typo? Anyone chime in? Does it seem fine to you? Does that look legit on the right side of the equal symbol to everybody? It shouldn't.
There's 2 7s.
Well, yeah, that doesn't matter. We can ignore one of those 7s. I'm talking about like an actual typo, like a typo, like this is not, to the right of that equal symbol, I don't have a set. In fact, because something is messed up. Nobody? Okay, what is the, okay, this is a left brace. Where's the right brace? It's right there. Here, this is a left brace. Where is the right brace?
Oh, that 1 7 doesn't have like the other side of it, the other parenthesis?
Yes, there should be a big ass curly brace right here. My pen is too far, so I'm not drawing it, but you can see my cursor, right? There should be a big ass curly, right curly brace right here to go with this one. Why? Because this curly brace here is the right brace for this left brace, right? This is one object, one element in the set. So I really should write a little brace there, but my pen is really, really far, like ridiculously far. It's like in the piano room. So put a right curly brace here in your notes. So that's why there's three things in here. There's the number 7. There's the set containing 7. We can ignore that because that's a duplicate. Then there's this big ass thing. And then end curly brace. Okay, good to find that typo. I'm surprised no one spotted that when we had class.
Don't do it.
So the inclusion-exclusion principle is this crazy formula. Let's say we have two sets. How to say how many things are in S or T? Well, we count the numbers of things in S, we count the number of things in T, and then we say we've overcounted by stuff that's both in S and T. So let's subtract that once. Actually, this is a good thing to show with. Actually, no, I'm not going to go to the chalkboard yet. But there's an easy visual proof using Venn diagrams why this is the right formula. So let's maybe look at this example. There's 4 things in S, these 4 things. There's 3 things in T. If I wanted to do the yin-yin, it's clear that the yin-yin has A, B, C, D, and E. 5 things. But if we wanted to do it the really hard way, we would count the things in S. There's 4 things. Count the things in T. There's 3 things. And then we say, oh shit, we've counted a couple things twice. What did we count twice? Well, the letters C and D is in both of these sets. So we subtract that exactly once to make up for the overcount, and we have 5 things. Okay, more in review. This is the real meat of why we study this stuff. The real meat is because of word problems. We have 1,000 students enrolled in math or English course. Suppose 400 take both math and English. 600 are taking English. How many are taking math? So remember, 600 are taking English. That sentence is not saying that those 600 are not taking math. Some of them might be taking math. So we create some mathematical terms to make this word problem into a math problem. Capital M is the set of students taking math. Capital E is the set of students taking English. And then we write out the inclusion-exclusion formula. The number of things in M union E is the number of things in M plus the number of things in E minus the number of things that are in both. Which numbers do we know? Well, we know from this sentence, 1,000 students are enrolled in math or English. We look at this symbol as the word or, so that must be 1,000 people in math or English. How many people are taking math? Well, we don't know that. That's what the question's asking. How many people are taking English? Well, that's right here, 600. How many people are taking math and English? Well, that's said right here, 400. So we throw all those buggers in, and then the number of things people taking math is 800. And as we recall from my lecture 3 weeks ago, pre-pandemia, the reason why more people are taking math than English is math is awesome. Woo! Yeah, okay. Nothing wrong with English. But yeah. Okay, so Augustus de Morgan, no relation to Morgan Freeman, although who knows. This was 1700s. There was a law for sets. If I take the prime of a union, it's equal to the intersection of the primes. So again, the complement of a union is an intersection of complements. So read this in English. This thing on the left says things that are not in S or T. And that's equivalent to things like on the right here, things that are not in S and not in T. So this sentence below here on the left, this says things that are not in S and T. So that's equivalent to I am not in S nor am I in T. So neither in S nor T is the way we read this. This or becomes more in English nor. Neither in S nor in T. Not in S or not in T is the same as not being in both of them. Okay, so that's Augustus de Morgan's contribution to logic and set theory, and it's called the Morgan's Law. And we can use this in any word problem. Just look this over again, students who missed this class, but it has applications. This example is a little bit long to get into, but I think the solution kind of speaks for itself. And then there's Venn diagrams or Venn diagrams or bubbles. We can use graphical representations. We have mammals and fishes. Here, some things are both mammals and fishes, like vertebrates and having a skeleton are characteristics shared by both mammals and fishes, but no mammals have scaly skin, no mammals are cold-blooded, and consequently also no fish have hair or fur, and no fish are warm-blooded. Although I feel like I've seen some furry-looking fish. Okay, so we shade the thing that we're talking. We shade all of S. We shade all of T for capital T. For the intersection, and then set theoretic notation, all the X in the universe, this line is read as such that X is in S and X is in T. That would just be the overlap. And similarly, the yin-yang is the easiest thing to shade. I said this over and over and over in class. You never use your brain to shade this. When you see this symbol, shade all of that, shade all of that. If there's intersection, who cares? Just shade it all. This is a no thinking game. This is a thinking game because you need to think. Well, what's in both? Here you don't think. You just start like being a robot. I'm going to shade all of S, then shade all of T. So you just do that. T prime, you can put your thumb over T, and then you can just say everything that's not T. What's that? Everything. Remember, the universe, by the way, in all of these is everything inside the rectangle. All the stuff inside the circles and outside the circles. So not T is I'm going to shade all this stuff inside the universe such that that stuff is not inside T. X is our dummy variable. All in the universe such that X is not an element of capital T. Okay. Then there's things that make me say the word wedgie. For example, this S intersect T prime is everything in the universe, all the X in the universe, such that X is inside of S and at the same time outside of T. So what's inside S and at the same time outside T? Well, what we do is we take the picture of what S looks like on the previous page, and then we take the picture of what T prime looks like, which is right above us, and where is the overlap of S prime from S from the previous page and T prime? Well, it's mainly this left wedgie. Right there. That's what the moon looks like sometimes when it's waxing or waning or one of those words. Okay. S prime union T prime is, remember, we just be like no thinking. Just shade all of S prime, then shade all of T prime. If there's overlap, great. Who cares? But the easier way to think about this is that this, by De Morgan's law, S prime union T prime is simply the prime of the intersection of S and T. Intersection of S and T is easy to draw. So if I take the prime of this whole rectangle, I just invert all the shadings, and that's the shading for this. So that's how you more easier think about this complicated looking thing. We just say that is equal to the prime of a simple picture. So there we go. I think we've learned everything that we've done. Oh, there's one more page. Things like by nerds, gots, and jocks. Ignore this. This needs to be updated because Dave Matthews, nobody knows who that is anymore. And I don't think RPGs is a gun. I think, or role-playing games something. Yes. Yeah. Apple product. Oh, yeah. Okay, ignore this. This is like, yeah. Okay, so important stuff. It's now 12:30, and we can get through this 5.3 stuff. So the homework on this is due Wednesday again. So the very first, oh gosh, I don't remember. There's a ton of problems that look like this in the beginning of section 5. Anyone remember? Wait, just chime out. These shading problems in web work. 5.2? 5.3?
5.2, I'm pretty sure.
Okay, and it's like the first 8 problems, right? Or something?
Yeah. Yeah.
Okay, so this is good to know because you only get full credit if you get it right on your first try, because there's like a multiple choice and you have to guess what the right answer is. So, and I think I cap it at 2 attempts and then I think it closes. Maybe I did that. I definitely did that. Okay, so we want to shade whatever A prime union B. Oops, did you hear me burp? Oh, not. Intersects C. So, way to do this is to first draw, well, PEMDAS. remember PEMDAS, please execute my dear Aunt Sally. It works for here too. Parentheses you do first. Parentheses says the union of A prime union B. So we draw that. What's A prime? Well, everything that's not this circle. So all of that got shaded first with these 45-degree angled lines. And what's B? Well, it's all these with these shaded lines. It looks like, well, they're shaded this direction with a negative slope. And there is overlap between these negative slope lines and these positive slope lines, namely these two areas. But we don't care. Yin doesn't give a damn about overlap. It says all the merrier. And then we want to draw the picture for C. And that's this bottom picture. And what's the intersection? Well, we take this picture, superimpose it above that with our psychedelic mind, and try to imagine that. Where is there common overlap? And I believe that it's these three sections. So that's one way to do it, and that tells you exactly why this shading is exactly that. There's another way to do it I explained in class last time that has got less glory, but will get you the right answer. Let's name the regions like this. Let's just name the regions 1, 2, 3, 4, 5, 6, 7, and 8. And then we're going to do this numerically. What's A intersect B? Well, A intersect B is the numbers regions 2 and 5. So what's the prime of that? The prime of that is everything that's not the number 2 or 5, which means the numbers 1, 3, 4, 6, 7, 8. So that's what's left of union. To the right of union is 4, 5, 6, and 7. The number C, letters set called capital C. The union says write all of these 6 numbers and then also write all of these 4 numbers. If there's overlap, don't write it twice, just write it at least once. And that gives us these, so the union of these 6 numbers and these 4 numbers is not 10 numbers, it's these 7 numbers because 3 of them obviously are in overlap. 4, 6, and 7 I'm not going to write twice. So then I start shading all of the 1, 3, 4, 5, 6, 7, 8, and that's why we get this drawing that's basically everything but the little top here, which looks like the hat that the Pope wears. Okay, so there we go. Boopity boom, and now we're on the new stuff finally. Woo! Okay, so I've got a new and better way to do this because I can't use the computer and a pen at the same time. I'm going to go low tech and do this, Jabby. Rotate. Okay. So I think you can also Control ++ on your screen if it's not big enough, or maybe I can just Control ++. How about? Oh yeah, there we go. So we'll look at this one first. I'm shading A union C prime union B. So this one might be easy to do just without even writing anything, but I'm going to do some work. Let's see, can I hide all this other stuff? Oh, there we go. Okay, so the symbol for A is just this shading. And then the one for B is, sorry, for this stuff. Well, first I'll do C prime, which is everything that's not C. And then I'm going to shade what B is, and B is this stuff. So then we look at these two drawings, and we're doing the union of that. So what's left unshaded? I guess most everything is almost shaded. Is there anything left unshaded? It looks like this part. Looks like this will not be shaded. And it looks like that's it, right? That's it. Before I shade, can any one person say, yeah, that's the only thing left not shaded in the union?
Yeah, that's the only thing.
You believe that? I believe that. Okay. By the way, it doesn't tell me who talks, so that voice sounded like F sub N of X. Was that?
Yeah, that's me.
Oh, what do you know? I know your voice. Okay. Boopity boom, boopity boom. Okay, Doporama. That's it. That's how we do that. And then here, we have a cursor in the way. Get out of the way. I'll put it on my forehead. Okay. So A intersect B prime intersects C. So we need two drawings. This drawing here will be A intersect B prime. So this is a wedgie, obviously a wedgie, right? Inside of A and at the same time outside of B. So inside A and outside B is this wedgie. So that's definitely inside A at the same time, not inside the B. I guess it's bad form for me not to name these things. Okay, so then what C is this jammy over here. Wow, wow, wow. And the intersection is clearly just this little tiny bit. I'm not even going to ask anyone's help. It's so obvious that this is where they meet. It's like the Pope's hat, if the Pope was like lying down. And it's like his hat. Okay. Oh, there we go. I believe that's correct. So let's zoom back. Okay. So that's that stuff. And then we move on to 4 applications. Let's see. Wait, this should be zoomed. So we're going to write down the elements in the following sets. A union B. Did I really not do this in class? I can't believe this. Okay. You know, just for some class participation, can someone tell me what A union B is in size order? Just the first one to chime in. Just anyone. Don't be shy. Should I call on someone? I don't remember who's in the room. Grace, are you in the room? Anyone? Oh, come on now. Tell me what the union is. Gosh darn it.
0, 1, 2, 3, 8.
2, 3. In size order, there's another one in B that's not that before the number 8.
Oh, 5.
There's one smaller than that too.
Oh my gosh.
Hint.
Oh, 4.
Okay. 4.
8.
Why are you skipping a little 5 here?
5, 8.
Why are you skipping a little 6 here?
5, 6, 8. I'm sorry.
Okay, this is fine. There's a pandemic. It's all good. I mean, this is Armageddon days. It's like, yeah, all good. Okay, so B prime then is everything that's inside the universe and not in this set. So I trust you all can do this. Say numbers that are not 0, 2, 4, or 6. So I'll just do it. 1, 3, not 4. 5, not 6. 7, 8, 9, 10. That's B prime. The intersection of A intersect B prime. Of course, this is a lot easier if I just did a damn drawing, first of all, because I know that this is a wedgie, but I think we can do this without a drawing. We want to be inside of A and outside of B. So outside of B, let's do a little scratch work. B prime is, oh, shit, I already did B prime. It's right there, damn it. Okay. So what's inside of this set up here and this set down here? Well, obviously they have a 1 in common, a 3 in common, and a 5 in common, and an 8. So 1, 3, 5, and 8. 1, 3, 5, and 8. So we want to be, in this question saying I want to be outside of A or inside of C. So again, this is a no thinking zone. So we just write everything in A prime, first of all. And A prime is the things that is not this stuff. So in the universe, but not 0, 1, 2, 3. Well, it looks like we have a 4 in A prime. What else do we have in A prime? 5, 6, 7, 9, 10. These are all the things in A prime. And now I write the run stuff in C. C is 1, 3, and 7. Well, I already wrote 7. So all I need to do is write the 1, 3, and the 5. And the order doesn't matter. Right, so this is fine to write it this way for web work, and for me it's prettier if the 1 was first, not the 3, but who cares? So here I have A union B prime, or I can write this by De Morgan's law as A prime intersect B prime. And why am I choosing that way? Because I already know what A prime is. It's right here in our face. What's B prime? It's right here in our face also. So what's the intersection of our two faces? Well, let's see. A prime is this stuff. B prime is this stuff. Looks like they have only the numbers 7, 9, and 10 in common. So that's what the intersection is, 7, 9, and 10. So it was clever to use De Morgan's law, by De Morgan's law, rather than looking at this set, which would require us to do the union and then say what's not inside the union. This is easier because they're the exact same thing. The prime of the union is the intersection of the primes. Okay, then we have this big bugger. A union C intersect B. So A union C we'll write first. A union C is this set and that set. So I'm just going to write everything in size order. 0, 1, 2, 3, 5, 7, 8. And I'm going to intersect that with B, which is 0, 2, 4, 6. And we get, what's their commonality? Looks like 0 and 2. Joy. Yay. Okay. If you have questions, just yell them out. If you don't, then that's fine too. Okay, so in these examples, we were given the symbols here and saying what's the contents. Here we're going to be given the contents, and we're going to say what's the symbol. Now, the symbol is not going to be one answer. Like if I said the set containing 7, 9, and 10, what is it? There's two answers. There's this answer or there's this answer. They're both equivalent answers. In fact, there's more answers. I could have also written this as A prime intersect B prime prime prime. I mean, this is the exact same thing as this left thing, which is the same exact thing as this thing. Why is this? Because a prime of a prime, they cancel each other out, right? So there's more than one way to express this with letters and symbols. So we'll just look for any one answer for the stuff below. So here we have, so we're going to say these are not contents of the set. The set A is not containing 2 and 3. What this diagram is saying, we're saying that this is region 2, region 2, region 3, region 4, region 1. So region 3 can be written as A intersect B. So regions 1, 2, and 4. So if we imagine 1, 2, and 4 are shaded, well, we don't have to imagine that. I can draw that. So region 1 looks like this. Region 2 looks like this. And region 4 looks like this. Well, then that obviously looks like the complement of something very popular. It looks like the complement of the intersection. So that's what we would write. The answer for that is clearly, this picture is clearly the intersection's complement. Again, that's not the only way to say this. We could have written this as A prime union B prime. But this seems more clear in words when I look at this picture. What is this? This is everything that's not inside the commonality of A and B. Like outside of the intersection of A and B is what's shaded. And here we have outside of A or outside of B. Yeah, that's true, but it's not like obviously true, as obvious as this sentence, this mathematical statement is. Okay, region 2 is just the wedgie here. The wedgie here on the left. Well, I can draw it out if we must. but that's clearly the stuff that's inside of A and at the same time outside of B. Region 1 is just the outside world. The outside world is stuff in the universe that's not in A or in B. So we can say that. I mean, I basically said the answer by saying the stuff in the universe that's not in A or in B. So what does that mean? Not in A or B. That's clearly what this drawing is. Not in A or B. Oh, this is the person who's going to write me to tell me what to do, like, about the recordings for this class. Okay, well, it's happening now, Kelly. Okay, cool. I don't know if you guys saw that, but actually, just question: do you guys see stuff like that that pops up? Like, any one person? It said I had an email from Kelly from Barron County UW campus.
Yeah, we can see it.
Saw that. Oh my gosh! So I should probably turn my email off in case like something crazy happens, like someone says your shipment of like crazy like weapons of mass distraction are ready to be shipped to you. I'm not ordering weapons of mass distraction, but okay, boop. That won't happen anymore. Okay, regions 1 and 4. So those are two different wedgies. Regions 1 and 4. That's this jammy here. And this jammy here. Oh no, that's the wrong drawing. Bummer. Regions 1 and 4. Okay, I'm going to ask you about that anyways. Regions 1 and 4. Well, 1 is this thing on the outside. And 4 is this thing here, this wedgie. Well, this is a dumb one to end on. Why? Because it's too simple. This is obviously everything that's not in S. This is not in A, I mean. A more interesting one I probably should have asked is this one, regions 2 and 4. Anyone have any ideas of how to describe this? This is kind of a challenge question because everything was kind of simple except for this. Well, we know how to make the left wedgie. That's A intersect B prime. But now I need to like also have the right wedgie, you know? I mean, there's multiple correct answers for this. Does anybody have any thoughts on like how we would like describe this? Nobody has any thoughts? We really know how to say this. That's that here. How do I say this? How do I say this wedgie? Okay, my new question. How do I describe this wedgie in terms of like stuff like that? Anybody, please, anybody who's awake. Come on, come on. Hey, Food Gal, are you there? I'm gonna eat a salad, damn it, today. You should at least speak up. Maybe you're not there. Is anybody there? Wait, did I just lose everybody? Hello? Hello? Is anybody there?
Yeah, we can hear you.
Well then why? Damn it! Okay, what's going on? Why is no one piping in about what this set might be called? Is that because
What was the question?
Oh, jeez. What is this set over here? How do I describe this set? Just this one here, just this black wedgie, this blue wedgie.
B? Just.
It's B, but it's more than that. Look at this example up here. This wedgie here was called A intersect B prime. So this wedgie here should be called
A intersect B?
A intersect B is just the middle stuff. So no. I'm going to give it to you because I'm going to blame it on pandemic. This here is called A prime intersect B. Because what is it? It's not in A and also in B. So I want to be inside of B and outside of A. That's clearly what that wedgie is. And this wedgie is clearly inside of A and outside of B. So what is this full drawing? The full drawing is the yin-yin of these two sets. That is the hardest question that can possibly be asked in this handout, which is why I was asking you peoples. This is a way to describe it, not the only way to describe it, but it is one way to describe it because we literally describe the left wedgie as that, the right wedgie as that, and then we take the yin-yin. Because the yin-yin says, shade everything to the left of me, then shade everything to the right of my symbol, yin-yin. And that's what this drawing is. Okay. Let's take a peek at this. So this is not Kentucky Fried Cat. This is just a regular cat. And Fred the Goat was that thing. Remember Fred the Goat was that person that I named that's Jesus' favorite goat. Bah, bah. Okay. So again, we have this type of question similar to what we did before, but now we have 8 regions. So region 7 is the triple intersection of A, B, and C. It's everything inside of A and inside of B and inside of C. That one is clear. Region 1 is the outside world. The outside world is everything that's not in A or B or C. That's clearly written as, so I'm outside of A or B or C. Equivalently, we can write A prime intersect B prime intersect C prime. So this is like De Morgan's law on crack, right? It's like a triple version. I'm not in A and not in B and not in C. So that's the same as saying I'm not in any one of these, A or B or C. Okay, regions 1 and 4. 1 and 4 is everything that's outside of the yin-yin of A, yin-yin B, clearly, right? I'm not going to draw this region because I think if we shaded 1 and we shaded 4, we'll see that everything is shaded except for my thumb. Oh, sorry, except for these two things. And those two things is A yin-yin B. So I would write A yin-yin B prime. Whoops. A yin-yin B prime. Or equivalently, another answer. Nobody's chiming in. But by De Morgan's law, I can write this as, anybody? Any of you 13 people who are awake? Come on! What is this equivalently by De Morgan's law? This is... Oh, come on. Please? Anybody? Aaron, are you there?
Yeah. A prime intersect B prime.
Okay, maybe I have to call on people. Oh, that's it. Luckily, I don't need to. You know what? It's all good. It's all good. Thank you, Aaron. Appreciate that. Okay, region number 2 alone only. Well, that's clear. Region 2 is, actually, that's not clear. This is a strange wedgie. Let me just draw it out. So A, B, C. So this wedgie, I want to be in A, and at the same time, I want to be outside of B or C. Well, then by just saying those words, inside of A, and at the same time, I want to be outside of B or C. I want to neither be in B nor be in C. So this is neither be in B nor C. So straight up, English helps us write the set because I'm inside of A and I'm neither in B nor C. And that's clearly what this is, inside of A, not in B or C. Okay. And then lastly, regions 4, 5, 6, and 7. Let's draw that out because that seems complicated. A, B, C. So region 4 is this bottom thing. Region 5 is this left pope hat. Region 6 is this right pope hat. Region 7 is this triple intersection bit. And then lastly, region 8 is the other pope hat. Okay, now I gotta admit this is hard. It seems like we got all of C, yin, the top of this hat, this pope hat. So C, yin, the pope hat. But how do we just get that pope hat? It's gonna be really hard just to get the hat of this pope. But I can get the whole football, like this whole thing. And it's okay, overlap is fine. That whole thing, this football that I'm looking at, is A intersect B. And I'm gonna yin this now with C. And you're gonna say, oh shit, but you overcounted. It doesn't matter, yin doesn't care about overcount. So I counted this part twice, but it's not counted twice. Remember, yin is all the stuff there, all the stuff there. If there's overlap, count it once, you know? It's all good. So this is an appropriate answer for this head that's wearing a pope hat. All right. We are on the finish line of this handout once we do this problem, an inclusion exclusion principle problem. So A intersect B are sets such that the following holds. They have 6 things in common. The size of A, there's 14 things in A. There's 40 things that are in A or B. So the question is, how many things are in B? Well, we can do this 2 ways. We can use the exclusion inclusion formula, which is kind of boring, or we can do a Venn diagram version, which is fun, I think. But let's do the boring version. A union B, the size of A union B is the size of A plus the size of B minus the size of the intersection. So we know how many things are in the union. There's 40 things here. Things in A, there's 14 things here. Things in B, this is a big mystery. We don't know that yet. That's what the question is asking. And the intersection has 6 things. If we put this all together, we have 14 minus 6 is the number 8. So 40 equals 8 plus the size of B. So that means that the size of B is equal to 32. Woo! So that's one way to do that. Now another way to do this is Venn diagram. So we draw a diagram of with 2 bubbles, a bubble and a B bubble. We always try to do the intersection if we know what the intersection is. And the intersection has 6 things in here. Remember, the goal is to count everything in size of B, this full circle. So, what do we know about left wedgie? How much stuff is over here in this left wedgie? Anybody? Please. If the size of A is 14, what's in this left wedgie? Turn on your mic.
14.
14 is the number that goes here. That would be bad because then I would say 14 plus 6 is 20 things in A. But there are not 20 things in A. So 14 is not the number here because then that would mean there's 20 things in A. So what's the correct answer for what goes in here?
8.
8. Yes, that's how we do this. I'm so glad someone said 14 because that's the popular mistake. 8 plus 6 is 14. So now we have what's in there. So how do I figure out here? We can't figure it out yet. But we do know that the union is 40. So that plus that equals 40. If this all adds up to 40, this number here has to be, well, 8 plus 6 is 14. And if I want to add all of this stuff up to 40, if 14 is here and that plus that is 40, that's 14. This number better be 26. Yes, now that plus that is 40. So now what's the size of B? Well, I can look at it. It's 6 plus 26. So the size of B is 6 plus 26, which is 32. And woo! See, I think this is the funner way to do this problem. And this is a way that gets the correct answer really fast. But is there any glory in that? I don't think so. So we're done with 5.3. The next handout is kind of like a baby review of how to do chapter 5.1 using Venn's diagram. So I'm kind of planning on skipping that and just doing 5.4 tomorrow. I'm going to stop sharing the screen and go back to here. Oh, wow, we're only down to 8 participants. We started with 14. We lost 6 people. Okay. Rebecca Barrett left the session. Okay, that's what I saw. I don't know if you see that. Okay, there's not much else to say. I guess I'm going to stop the recording. Does anyone have any questions they think that the recording people might enjoy hearing before I stop the recording? Anybody? Nobody. So I'm going to stop the recording.